I'll have one on undergrad. I think it's every time. Two postdocs, we're still struggling with getting our side and they're making
well, all the others
I've complained like crazy.
they got the infrastructure and the service runs along the backside of the
Okay.
Run a lot of that. They ran out of money.
Let me have your attention. Let's get started. Welcome to the University of Tennessee Nuclear Engineering Department Seminar Series. This is our last scheduled seminar for the semester. We sincerely hope you've enjoyed our seminar program this year, and we're looking forward to the seminar program next year. Before I introduce the speaker, I have some students I'd like to recognize. In particular, we had about 25 students attend the National Student Conference about a week ago. It's one of the largest contingencies at the student conference, I'm told. And 5 of our students were recognized for presenting outstanding papers. And although some of them are undergraduates and are probably not here, I want to recognize both the undergraduates and the graduate students who received outstanding paper awards. The undergraduates were Bart Lynch and Christina Campbell, who are sophomores in nuclear engineering. They had a paper about their freshman experiences in our new engineering freshman Engage program, and it won an award. And then Shane Parkey, he's a junior in nuclear engineering. He had a paper on his experiences as a co-op student at Nuclear Fuel Services in the area of criticality safety. And then we had 2 graduate students that got recognized, and they are both here in the audience. One is Zal Key, and the other one is Patrick Planahan. They both talked about their research projects for their graduate degrees. Let's give these students a round of applause. Stand up. Stand up. Stand up. Okay. Thank you. Today's speaker is Dr. Patrick Taylor, who is professor and head of the Department of Materials Science and Engineering here at the university. He is a registered professional engineer and a fellow of the American Society for Materials. He was educated at the Colorado School of Mines, where he received 2 BS degrees, one in metallurgical engineering and one in mathematics, and then a PhD degree in metallurgical engineering. He has supervised the research of more than 50 graduate students and published over 100 papers, and he has received 5 patents. The title of his presentation today is Research on Vitrification of Radioactive Waste. Welcome. Thank you.
Well, it's a real pleasure to be here in this department. I didn't realize before I came here what a good nuclear engineering program you have, but when I came over to one of the seminars a few months ago, I saw that some of the research the fellow was talking about was a lot like the work I've been doing for British Nuclear Fuels over the last few years. So I thought it might be informative for me to talk about a couple of my recent research projects for British Nuclear Fuels. And it has 2 purposes. One, to, of course, brag about my research, but 2 is to look for collaboration or areas where maybe we could do some things together in research or education. So, start. Wrong arrow. The first talk is on the characterization of iron phosphate wasteborne. Mr. Wong had gone to work for a fiber optic company, but he worked on this for a PhD project. Whoops. Part of the requirements for a vitrification system requires that we really have an understanding of what are some of the important properties. And you might use a system approach for vitrification, which includes an understanding of economics, although the economics here really relate to the goals. We'd like to have high waste loading, large volume reduction. And there are a number of process-specific factors that one has to understand. But in order to be able to do it, that is, to make a vitrified glass, there's a number of processability requirements that one has to develop in order to be able to do this. And they include things like understanding melt viscosity, understanding the volatility of hazardous species, and the solubility of waste components in the glass forming. And so what I'm going to talk about today is a laboratory that BNFL paid for, and we developed to look at things like melt viscosity, melt density, volatility of hazardous species, and waste solubility. And all of this then, of course, has to be evaluated in terms of performance, which is durability, homogeneity, and mechanical stability, and so on. So we're talking in this particular research about this part of the research. So the research objectives are pretty straightforward. We want to develop an experimental system to measure high temperature viscosity of molten glasses and slags, density, and partitioning behavior of simulated radioactive waste in vitrifying media at high temperatures. We looked at a surrogate strategy because in our laboratory we cannot use radioactive materials. We have to identify the proper surrogates to use in these systems. We then looked at, among other things, iron phosphate as a waste form based on the interest of the company that's sponsoring this. And then we looked at the partitioning and solubility of various metals in the iron phosphate glass. Viscosity measurements are, of course, important to the viability of any process that involves a molten phase because it defines reaction conditions, melting rate, throughput, and pourability. And typically, you would like a glass in the viscosity range of 20 to 100 pulls. We developed, based on ASTM standard, a viscosity system. I'll show you a picture. That basically amounts to a spindle, and you use a viscometer and rotate, and a crucible, and this just shows a general design. What these are made out of is a very difficult problem, particularly when you're looking at very high temperature measurements. You may ask, well, why high temperature measurements? Well, a lot of the newer vitrification technology involves the use of thermal plasma and use glasses which potentially can have a much higher melting point or much different conditions than conventional borosilicate glasses. So we'd like to be able to determine some of these properties at elevated temperatures to see if some of these new technologies have some viability. And so we built a viscosity unit, and that's shown in a picture here. This furnace is a molybdesilicide element furnace, and it goes up to about 1700 centigrade. So it allows us to measure viscosity theoretically up to about 1700 centigrade. Shown here is a controller, but this graphite part here is really a support system for a crucible that sits here, and then the viscometer is shown coming down through here. This whole thing is on a movable platform that allows us to position the viscometer at the right level into the system, and then the data is taken here. This is a lot harder than it looks to build a system that operates up to these temperatures, but this is an example of a high temperature system for high temperature viscosity. Then we also have a lower temperature system. This one was capable of about 1100 degrees C, and of course, because of the lower temperatures, it's much easier to operate, just a similar kind of thing. In order to be able to determine whether or not your viscometer works properly, of course, you have to calibrate it. And there are ASTM standard glasses that one can purchase that the viscosity is known. And this is just an example of a viscosity in poise versus temperature in degrees centigrade, where the measured value from our viscometer versus the certified value is shown. This is over a temperature range of about 1260 to 1140 as an example of calibration. And this is another lower temperature calibration with boron oxide, which is pretty well known, where the viscosity and reported values are shown in the temperature range of 900 to 1,000 degrees. We'll look at some of the measurements for the real system in a minute. The next parameter that's important to measure is density. It gives us something about the liquid structure, but also is important to basic properties such as partial molar volume, volumetric expansion, surface tension, and kinematic viscosity, and it really has an effect on throughput rate and mass input and vitrification. And so a method to be able to measure densities is also very important. And we use this kind of modified spindle method where you put the spindle in a certain level and measure the weight. You put it in a little bit all the way through and you measure the weight. and then you subtract the two. And why that's important is when you have a solid in contact with a liquid, you have capillary forces by the liquid on the solid. So this allows you to subtract out the capillary forces from the measurement. The only difficult parameter is this thermal expansion, volumetric thermal expansion coefficient that needs to be known for this material in order to be able to do it. But the density then is a fairly straightforward method of weighing a Plumbaugh kind of system as it goes into the reactor. And this is an example of calibrated values for boron oxide at 1,000 degrees. These are our measured density, and these are the literature values, and they're pretty close. Okay, partitioning. Partitioning, there's really a lack of information of partitioning of hazardous substance between the glass phase and the gas phase. And an understanding of this is really important in order to minimize volatility of those elements that might leave the glass and go into the vapor phase. And it really gives an idea about off-gas design. But in order to do that in a university lab, you've really got to come up with surrogates to avoid radiological work. The surrogates ideally would be non-toxic, expensive, easy to handle. And you do this by matching physical and chemical properties between the radionuclides and the things you like. And you can use things like thermodynamic or phase stability diagrams to assist in the match. And this is not going to show up in this slide, but believe me when I say that this is showing surrogate research. For example, cesium's no problem where there's a natural one. Strontium, of course, there is. But things like plutonium, we would use cesium as a surrogate potentially, and so on. But basically, this is intended to show the surrogates that are useful. This is not going to show up real good either, but this is the schematic showing the reactor system for these volatility studies. What we have is a crucible here. In this particular case, it says graphite. You heat this furnace up to whatever temperature with the material, the glass phase, and the material that you want to see if it stays there or goes into the vapor phase in there. You leave it there for a period of time. There's a thermocouple for temperature. There's gas that flows through here. It carries any vapors over to a water condensation bath where you collect that. You then have the initial composition. After the experiment's over, you take a small sample of this glass, you dissolve it, you run ICP, and you determine what's left over, and then you get an idea of how much was there. And this shows our experimental system. This is, again, a molybdenum furnace capable of about 1,700 degrees centigrade. This shows a flow meter, the gas, and a little water condensation system. So it's pretty straightforward. Let's talk about iron phosphate. Iron phosphate is a promising candidate for immobilization of waste containing high contents of phosphate, halides, actinide, and heavy metals. And these are just some general properties for iron phosphate. Its composition is 40% Fe2O3 and 60% P2O5. No viscosity or density data or partitioning data existed before, I think, this study. So you take some, mix up 60% P2O5, 40% Fe2O3, and you put it in the viscometer, and you start increasing the velocity of the viscometer, and the viscosity changes. Well, that's not good. We expect, as most of you know, viscosity to be constant with shear, with the Newtonian fluids. And this is typical of a non-Newtonian plot where you speed up the system and then you decrease it, and you look at how the viscosity changes both during increasing rates of shear and decreasing rates of shear. So right away we see this as a non-Newtonian fluid. Which from a process engineer's point of view is not a great thing. You can do this in terms of shear diagrams. This is the shear stress, this is the shear rate, and this line, lower dashed line, is intended to be the Newtonian plot. And you see that there is this little initial amount of shear that has to be put into the system to get it flow, and then it acts kind of Newtonian after that. It's just kind of like a Bingham plastic or whatever. And this is just for various experiments during startup and shut down. Well, that's interesting, but if we start with ammonium phosphate and ferric oxide with the right proportions to make this 60% P2O5 and 40% Fe2O3, and you look at this is RPM and this is viscosity, and again, I'm sorry if you can't read it in the back. The light here is pretty low, but basically it is Newtonian. There's no difference in the viscosity versus shear in this system. So we have one system where we started with certain precursors that's non-Newtonian. We had another system in which we started with ammonium phosphate and iron oxide, which is Newtonian, and we got to question whether or not there's some differences. But giving the second set of data, you can plot viscosity versus temperature. This is 80 to about 20 Foys over a temperature range of about 1050 to 1150 centigrade. Or you can plot it with an Arrhenius type equation and actually get an activation energy of viscosity, as shown here for the second stage. And this is the kind of data that a process engineer really would like to have, to know the viscosity under certain temperatures, to be able to predict flow rates and ability to move this material. So we wanted to compare these two systems, and it became a question of why were they different? Well, material scientists like things like X-ray diffraction and inductively coupled analysis and so on. So we used a variety of techniques to see if there were differences in phase, structure, and composition. And it turns out there are, because of the way these things are formed, the thermal histories and starting material, which really led to question that you have to be very careful when you're making this material to make sure that it has the right properties that you want. And I'll show you a few examples of that. Thermal histories were slightly different, but at the ICP results for the ammonium phosphate Fe2O3 system, it was basically, when we were done, about 38.2 mole percent Fe2O3 and about 61.8 P2O5. But the phosphorus oxide was a little higher in the iron oxide and lower in the iron oxide, which they're about the same. You wouldn't expect any difference. But if you look at them visually, this shows just taking a glass tube and dipping it in the material. This is the material made with the ammonium phosphate. This is the one made with phosphorus oxide. There's an enormous difference in the two, as you see structurally. But if you use X-ray diffraction, the only phase identified here is FePO4, which is a phase we want, iron phosphate. Whereas in this one, it's a combination of the FePO4 but another phosphate phase, FePO3 too, and a little bit of alumina. But, so chemically they were different because of the starting materials in the system. A little bit about partitioning. One of the big advantages of iron phosphate over conventional glasses is, according to people at Rolla, University of Missouri Rolla that work quite a bit on this, is that they have a larger ability to accept strontium or cesium into the glass phase. And these show some partition experiments. This is the amount of strontium in the gas phase versus that amount in the slag or glass. And this is talking about 1% or 1.2%. So we're talking about maybe losing 1% of the strontium that was in the glass initially versus the amount of strontium that we can load into the glass. And this is about 10 to 12% strontium in the iron phosphate glass. And what this shows is that you can load very high amounts of strontium into this iron phosphate without large amounts of volatility. And if you follow some of the vitrification literature, you'll know that strontium volatility is a problem in many of these glass systems. Similar thing for cesium. This is again 2% weight loss from the glass phase at about 12 or 13% loading into the system. So this is an example of a vitrification study where we found that the solubility of cesium, strontium, and phosphate glass is significantly higher than associated with borosilicate. These are promising candidates for mobilization. The addition of these common weights don't appear to alter the basic features, and the glass structure may contain interstitial voids which are large enough to host these larger atoms. Talk again about another project that we had for them. This one was on radioactive waste vitrification using a thermoplasma-fired cyclone reactor. There's a variety of mobilization technologies that one can use, and a variety of wasteforms that one can attempt to make, things like crystalline wasteform, glass ceramics, cermats, grouts, geopolymers, or vitreous forms. All of the vitreous forms that are made by dual ceramic heating or plasma or so on are really the type we're talking about here, although these others have some real potential in certain applications. So the glass quality is defined between a balance between the product and process reliability. Again, what we like is chemical durability, thermal stability, mechanical durability. But the processing, it depends on residence time, viscosity, waste loading, melt temperature, corrosivity, volatility, those things that we were talking about before. So developing processes that allow us to make a reliable product that also take into account the processing considerations is very important. We need to have an understanding of a variety of things that affect the waste glass preparation, and we just talked about this. Viscosity, we didn't talk too much about these aspects, but the processing properties and the durability issues were all very important. Waste glass melters are designed typically as integrated systems. They designed to prevent contamination and irradiation of the surrounding environment. You try to limit the maintenance problems, replacement of auxiliary devices, and you have to do operation and repair remotely. There's usually a waste, a feed preparation system, a waste glass melter, canister, and effluent treatment. Show a couple examples. This is an induction heated melter. And again, I'm sorry if you can't see this very well, but they use medium frequency radio induction, a nickel chromium melter pot, operates in the temperature of 1,000 to 1150, which means we need glasses that have good properties in this melt temperature range. Typically has a rotary calciner at the top, production rate of about 25 kilograms per hour. And at the time we wrote this, there was a new cold crucible design which might allow this to go to much higher temperatures, in which case you could use different glasses and increase the production rate of these systems. The other major type of system is joule-heated melters, which is shown here. Temperatures are typically 1050 to 1200. They're ceramic lined and slurry fed. They typically have a capacity in the reactor of about 6,100 kilograms. Takes about 59 hours of residence in the melter. Production rate of 104 kilograms per hour. And they're talking about mechanically agitated versions, but basically you have a chamber here, ceramic line, you've got two electrodes that provide the resistance heating. Everything's melted and then taken out of the system into a melter. Well, those are all good, but I have a better system. It's a thermoplasma system, and it has certain advantages over some of these. Plasma has the advantages of a clean, concentrated enthalpy source with very high temperatures available, accelerated reaction rate, melting rates, increased throughput, allows high temperature investigations for novel vitrifying media, fairly low gas flow rates to minimize particulate containment. You can feed liquids, powders, slurries, has high volatility destruction, is able to be operated remotely, compact, and portable. The disadvantages, it's perceived as an expensive technology and only suited for niche applications. There's relatively little data published on basic research. There's concern about torch electrode wear. You got this plasma torch in a radioactive environment. You don't want the electrode to fail every 5 minutes, and you have to go in there and replace the electrode, and refractory wear rate concerns. We built a cyclone reactor, but just as a bit of an overview, reactors based on cyclone geometry have been around since the 1940s. KIVSAT is an example. There are coal-fired plants that use cyclones, flame control, cyclone reactor, Contop. These are examples of commercial either ore smelting or energy-generating cyclone reactors. So it's not a new technology except in this particular application. So our objectives were to design, build, and evaluate a flexible, high-throughput plasma-based system for treating radioactive waste. This reactor had to do both calcining and vitrifying both in the same reactor, so you don't have a rotary kiln and then the heater, and would produce a durable, highly leach-resistant final waste form. This is what it looks like in a pictorial view. There's a plasma torch. In this case, it's a 50 kilowatt Plasma Energy Corporation non-transferred arc torch attached tangentially to a cyclone reactor. If you look at the internals, let's start here. The simulated radioactive waste is injected near the plasma flame, where you get nearly instantaneous dehydration, calcination reaction. A little bit lower down, you inject the glass-making frit. It forms a liquid falling film of glass. Because of the cyclonic flow, the dust is thrown to the wall, where it's captured by this falling film of glass and goes down to a chamber below, where it's collected in a temperature-controlled environment. The off-gas then goes off into the gas treatment system. This shows some quenching baffles just to bring the temperature down before off-gas. It's a laboratory system, of course, but it allows us to look at some important parameters as to whether this kind of technology might have some use for vitrification treatment. Materials of construction inside the top and these walls in the highly oxidizing zone are made out of castable mag oxide. The lower section where you have the glass is made out of nitride bonded silicon carbide, and we'll talk a bit about the refractory study. You don't want this to wear out very quick, of course. You might imagine, again, schematically what's going up is we have a calcination zone, and then we have a vitrification zone. Up here in the top part where we have the plasma torch, we have a very high temperature flame, and we're injecting the material into that flame zone. Because of the closed top, you actually form a recirculation zone where you get very, very good mixing right where that plasma torch comes in. So everything sees very, very high temperatures, fairly strongly oxidizing conditions. But a little lower down where you inject the vitrifying media, because of the cyclonic flow, you start forming forces that throw the dust or solid particles to the wall. So you have this glass frit which captures that and then goes down. This shows a discharge baffle where we put in some of these experiments to try to minimize the amount of material that might just short circuit through the bottom of this and go out of the system. We had built a plexiglass model of this. I didn't bring any of those slides, but a plexiglass model of the same scale. But basically there's a possibility of a short circuit of a certain amount of material that just comes in and goes down the center. There's a maximum velocity streamline that goes near the wall, goes in, and then goes outside the wall. There's a low velocity streamline that follows the wall. If you combine all three, that's really the behavior. So high velocity here, that really forces things into the low velocity region at the wall, which then acts as a capture. This shows the plasma torch attached to the reactor. It's about, these sections are about 18 inches, so it's about 5 foot tall. It's about 2.5 foot in diameter. These are just some gas water flow parameters, thermocouples, and so on. So basically you're injecting the simulated waste here, you're injecting the glass-making frit lower down and collecting material out of the bottom. This just shows the power supply and control system. This reactor has been relocated in my lab here, and it should be up and running, I hope, very soon. Refractory selection. What we did to study refractories, we actually took the lid of this reactor and we machined holes in it where we could put various materials into the top of this, and then we looked at what happened to this exposed lower surface. And so we looked at a bunch of different materials: stabilized zirconia, alumina, magnesium, nitride bonded silicon carbide, and so on. But it's really through a series of experiments with buttons in the top. The reason we did this is very expensive to reline this reactor with different refractories, as you might imagine. But we came up with the fact that magnesium oxide is best in the upper chamber, and nitride bond with silicon carbide is better in the lower chamber. Electrode wear. We used 3 electrodes during the first year of this, and that's really when we started looking at it. The first electrode, which is shown, I think, here, was damaged during our initial run, and then we modified the torch port. The second electrode, which didn't wear very much, weighed a little bit over 59 hours, and then we came up with a system that doesn't wear at all. We found out something interesting, is that we actually form a protective coating on the electrode from the sodium aluminate that we put into this waste. The sodium aluminate comes from, we were looking at the Hanford tank waste at the time. So we wrote a patent disclosure on protecting electrodes because we figured out if you can get this sodium aluminate to coat the surface, it greatly diminishes the wear. It acts like a local point that melts and then distributes the heat around the surface. so it's like a protective coating on the surface of it. And so electrode wear became less of an important, and this calcination deposit on electrode provides a protective coating, or at least we think we do, over the course of the experiments that we did. An example of the material that we looked at, the first one we looked at, this is a Hanford tankway simulant from Battelle. This is a borosilicate glass. This is basically the composition of the calcinate. So you take a simulated Hanford tankway and you inject it near the plasma flame, then you inject the borosilicate vitrifying media lower down, and what do you get? Well, these are typical experimental results. Run at about 30 kilowatts, where we're feeding about 30 grams per minute of simulant and about 30 to 60 grams per minute of the borosilicate glass. And these are the amounts of the simulant that we converted into the glass phase, range from 89 to 92. There is some carryover conversions, and these preliminary experiments were typically 80 to 90%. Conversions were typically 90% of the simulant ended up in the glass phase. The carryover, at least in these experiments, for primarily silica, is shown by this X-ray diffraction. This big peak here is silica, and there's some minor peaks of sodium aluminate that occur here in these particular experiments. Since we did these experiments, we did a series of experiments on things like interfacial cred from solvent extraction, patterned after the plant in England. We did some experiments on some of the waste, other waste streams that they identified. And so we developed a thermoplasma reactor. It was built, operated, and modified to study calcination, and that should be a V. I don't know. It's not vitrification. Vitrification of radioactive waste. This research was supported by British Nuclear Fuels. Dr. Bob Holmes and Dr. Sten Roden were the program managers. Thank you very much.
Okay, this presentation is now open for questions and comments. Okay, Igor?
Yeah, if the viscosity goes up as the rotational speed goes up.
No, that plot showed that at the viscosity was highest at the low rotation rate. So as you increase the rotation, the viscosity went down, and then it went back up as you slowed things down. Which is typical of, I think, a big and plastic type behavior.
The high temperature furnace, furnace, who is the vendor?
That was bought from a company called MHI in Cincinnati, and they sell molybdenum furnaces and the elements that you'd like. I can get you them. I have those furnaces here too, so if you need to use them, they're being installed. Yes.
I thought it was a weak fluid that goes down the axis. Is that because it's just gravitational fall, or is that a streamline?
No, there is a certain amount of the flow. We used hot water anemometry and a whole bunch of stuff in this plexiglass model to measure the velocity profile. There is a axial velocity component that goes down the center line of these cyclone reactors. The relative volume percent is pretty small, but there is a velocity component axially down the center line of closed-off cyclone. And typically they report in these type of reactors carryover of about 5 to 8% of the dust or material repeating short circuits. And that's why we tried to baffle to try to minimize the amount of short circuiting that happened in the system. Yes,
you were showing a 80 to 90% separation in your last slide there. Is that acceptable for a big unit, out there?
An ideal reactor would, of course, have less than that. And I think there are ways to improve the efficiency at which you collect material from these reactors. This type of reactor, I don't think will ever be a large production reactor. It's more suited for small quantities like orphan waste streams in a large plant where you can't just take it and put it back into your ceramic heater, or you have small quantities and you'd like to move a reactor from place to place. There are several considerations about scale-up. It's possible you can scale it up some, and we do in industry uses the fairly large production rate. But on this kind of application, it's always going to be pretty small application.
You have a comment?
What did you use to replace uranium?
I didn't use any uranium in this particular
No, that was here's a table, I think.
What was that?
There was uranium
I could
on the
go
left,
back.
and I couldn't tell what was on the right.
I can't remember. In the surrogate strategy.
Yeah, the surrogate.
I keep going. Uranium.
Cerium.
Yeah, Syria. I think both of these tables came out of literature reviews, not our own, but somebody else. I probably have them someplace. But in both, they say the rare earths would replace some of these. And in the lower one, the uranium's replaced by Syria. As you might imagine, I'm not a nuclear expert. I'm a process engineer, so probably.
Are there any other questions?
How does this compare with borosilicate glass that what's planned to be used for vitrification of hydrocarbons? I mean, in terms of its amount that it can...
The iron phosphate?
Yeah.
It's still a research concept. We're really based on some work done at the University of Missouri-Rolla, where they identified that this might be a good material to be able to capture some of these things like cesium and strontium and other phosphides and chlorides that borosilicates cannot deal with. Now, this is just a beginning of a research program to try to identify whether this has potential. Our contribution just showed that you can load quite a lot of cesium or strontium into iron phosphate without a large amount of volatility. If you try to do the same thing with borosilicate, you're not going to be able to get that amount into the system. So then it's waste specific. If you have a waste stream that's got a lot of chlorides or phosphates, cesium and strontium, you may want to consider the possibility of iron phosphate as a good factor. It's like a lot of research. It's quite a ways away. I think most of the commercial operation, like the floor plant and stuff, all use borosilicate type glasses to do this. But they have constraints on what they can put into that in terms of materials that they can keep.
Any other questions or comments? Let me remind everyone that this is our last seminar scheduled for the semester, that all of our seminar webcasts have been archived and are located on our website, and you can look at them at any time. All you need is a player like Real Player or Windows Media Player. And I used to say a reasonably fast internet connection, but I'm told that even a 56K modem, you can get a pretty good representation of video and audio of all of our seminar webcasts. So I just remind everybody of that. Let's express our appreciation to Patrick Taylor again for coming. And of course, we have refreshments downstairs on the second floor, and everyone is invited. Thank you.